So this is problem number 3. It's from the 2016 AP Calc A, B, and BC exam. And this is a non-calculator question where they give you a graph of a function f. And f is a bunch of line segments. And they tell us that this new function g is going to be defined as a definite integral that depends on f. So in part A here, they ask us whether or not g has a relative max, min, or neither at 10. Justify your answer. Well, to answer questions about relative maxes and mins, what we usually like to do is we like to see that the first derivative changes signs from either positive to negative, indicating a max. If our function goes from increase to decrease, we have a max. If our function goes decrease to increase, we have a min. And so the first derivative of this function g, using FTC Part 2, Fundamental Theorem of Calculus Part 2, the derivative of this definite integral is going to just end up being the integrand, f, with the variable that's in the upper limit of integration tossed in place of the t. So g prime is equal to f. So you see I kind of relabeled this graph here. Yeah, it's a graph of f, but it's actually also a graph of g prime since g prime is equal to f. And so if we have a relative max or min, the derivative has to be 0 or undefined. And if you think about g prime of 10, which is equivalent to f of 10, go to your graph, since it's really a graph of g prime, you end up seeing, yeah, g prime is 0 at 10. So it's definitely a candidate for a max or a min. But then if you look at the sign of g prime on either side, and keep in mind, this is a graph of g prime. Since g prime equals f, we've got a negative value on the graph of g prime to the left of 10. We have a negative value on the graph of g prime to the right of 10. Since g prime is negative both to the left and right of 10, you don't have either a max or a min at that x. Part B, similar sort of question, but now it's asking about an inflection point at 4. So here you'd have to think, all right, well, if I'm looking for an inflection point, I need to work with the second derivative because I need to show that I have a change in concavity at a certain location. So we had this from part A, g prime is equal to f. Well, taking the derivative of this side gives you g double prime. Taking the derivative of this side with respect to x gives you f prime. So the second derivative of g is actually equivalent to the first derivative of f. And so what you have to kind of recognize here is that to determine values of g double prime or values of f prime, you've got to look at slopes on the graph of f. And so if you think about points of inflection, we need a change in concavity from either concave up to concave down or vice versa. And in order for the second derivative to change signs, in order for that change in concavity to be present, we need our second derivative to either be undefined or 0 at the x value that's under consideration. Well, if you check the x value of 4, we do have a cusp on the graph of f at the x of 4. And because the slope changes instantly from a positive to a negative across that cusp, g double prime of 4 is undefined. If you think about what the sign of g double prime is to the left of 4, and keep in mind g double prime is equal to f prime, so we're looking at the slope of this graph. We've got a positive slope to the left of 4. We've got a negative slope to the right of 4. So to the left of the x value of 4 on the graph of g, our graph's going to be concave up because of the positive second derivative value, and then to the right we're going to be concave down because of the negative second derivative value. So yes, because the second derivative changes signs as we pass the x value of 4, we do have a point of inflection at that x. Part C is the most involved part of this question, in my opinion. It asks you to find absolute max and minimum values for the function g between -4 and 12, including both endpoints, and then of course to justify your answer. Well, since g is going to be continuous, since it's defined by this continuous function f, what we can use here is we can use what's called the extreme value theorem, and we've used that a lot. It basically says you will attain both a max and a min for this function on this closed interval. The max and the min will happen either at the endpoints of the interval, so candidates for the max and min are -4 and 12, and then also critical numbers within the interval. And so critical numbers within would be places where the derivative is either 0 or undefined. Well, since g prime is equal to f, we stated that back in part A, and we're really looking at a graph of g prime here. Our derivative of g is 0 at -2, at 2, at 6, and at 10. So the normal procedure from here would be to evaluate the function g right? We're looking for the maximum and minimum values of g. So evaluate the function g at each of these x's. Well, that's going to be quite a bit of work. You can actually cut out a few of those evaluations by recognizing, when we said this in part A, at 10, we don't have a relative max or a relative min. Since there's not a relative max or a relative min at 10, there's no way that could be the absolute max or the absolute min. Same thing actually happens at 2. We don't have g prime changing signs at 2. So it's not a relative max or min, therefore it can't be the absolute max and min. So we basically, these were candidates, 10 and 2, because they are critical numbers, but we don't have relative extrema there, so there's no way we could have absolute extrema. And from there, it's just going to be a matter of taking some time to evaluate these function values. So we need g of -4, so we toss -4 in place of the x and g, and it's kind of up off the screen here, but remember, x was that upper limit of integration, and so you look at this integral and you say, all right, well, I can do that using area arguments, since a definite integral computes a signed area between the function and the x-axis, but we only can use the signed area arguments that we know if the limits of integration are in the correct numerical order. So we need the upper limit of integration to be the larger numerical value. That's not happening right here. So we've done this a bunch. Swap the limits of integration, hang a negative out in front, and then you've got to take some time using areas of triangles to try and figure out the value of g of -4. And so if you think about g of -4, you've got this triangle right here that sits below the x-axis, and so the area of it is going to come back to us as a negative value. And then we're going to be looking at 1/2 base of 2, height of 4, and then the rest of the way to 2, what we see is we see this triangle. And so then that triangle is above the x-axis, so that's going to definitely be added on. And if we do 1/2 base of 4, height of 4, we end up evaluating this, getting an answer of -4. I'm not going to go through the rest of these calculations. It's just going to be using area arguments. All of these are triangles. Really the only thing you'd have to be careful of is any of these triangles that sit below the x-axis, like the one that we considered over here, the one that's here, the one that's here. You're going to have to make sure you have those taking on negative areas, since a definite integral by definition computes a signed area and not just an area. And if you evaluate all those successfully, you'll see that the smallest y value you get is at -2, and it happens to be -8. The largest value for g that you get back in return is +8, and that happens at an x of 6. Last part of this is kind of tricky. We'll probably go back and talk about some of the calculations we just referenced in part C to make some sense out of this. Obviously, don't have a lot of work on this screen, but what this problem asks of us is to try to find the intervals where g of x is less than 0. And so if you think about g of x being less than 0, we did a bunch of computations back here in part B. And if you think about what g of 2 is going to be, we kind of ruled that out, so we didn't necessarily evaluate it back here. But if you put 2 into this upper limit of integration in place of the x, the signed area between f and the axis from 2 to 2, well, there's no width there, so that's going to be 0. So at this x, the value of g is 0. So check out what happened whenever we evaluated at -4. Because we had to swap the limits of integration, what we ended up getting was a negative value whenever we took the opposite of this area plus that area. We didn't really do this computation back in part C. We didn't talk about it much, but we did evaluate the function at -2, and what you're going to see is you end up with -8 for the function value for g at -2. So the function value for g is negative at -4, still negative at -2. It doesn't get to 0 until we get to 2. So what we can say in part D here is that g of x is going to be less than or equal to 0 from -4 until 2. At 2 it is 0. And then if you think about moving forward from there, g of x is going to have a positive value at 3 because this area is above the x-axis. So if you put a 3 there, you get a positive value back in return. This whole entire triangle is above the x-axis. So from 2 to 4, the sign of g is going to be positive. And then if you think about these two triangles right here, these two triangles are definitely congruent. And so this triangle being above the x-axis and this triangle being below the x-axis is going to cause g to have a function value of 0 at 10, right? Because from 2 to 10, what we would end up doing to find the function value for g is we would end up computing this area minus that area. And since those triangles are congruent, that's going to get us back to 0. And then from 10 the rest of the way to 12, if we're at a 0 function value for g at 10, as we move forward to 12 and accumulate the rest of the area between this graph and the axis, since all of that region's below the x-axis, what we're going to have is we're going to have a negative function value again there. So it's kind of tricky. If we would have taken more time to really talk about part C here, I think that would make a little bit more sense. But I think if you just kind of think about the area arguments and some of the arguments that I just made, that this part should make sense to you too.